Hey there, welcome back. It's time to do some calculus on vector functions. All right, so in order to do some calculus, we'll need the concepts of a limit. So a limit of a vector function comes from taking the limits of each of its component functions. So if we have a, if we have, we want to take the limit as t goes to some value of the vector function. So we've got this vector function hanging around in outer space. Maybe it does a jump. Whoa! And so we go like this. We want to know, does the limit exist at some point? Well, we ask the question, does the limit exist in the x-coordinate? Does the limit exist in the y-coordinate? Does the limit exist in the z-coordinate? And if so, then we'll take the limit in the x-coordinate, the limit in the y-coordinate, the limit in the z-coordinate, and say that xyz vector is the limit of the vector function. So if it makes sense, then this limit, this point right here, uh, does exist, and it's called the limit. A vector valued function is continuous at a if this limit, remember a limit might have a hole, and this limit would exist, but what we need for a function to be continuous is if r of a is equal to the limit as t goes to a of r of t. Right? We want to make sure there's no holes, no jumps, all of those things that we're used to seeing that make functions not so nice. All right, so once we have a limit, we can define the derivative of a vector function. Well, we'll define it similarly to how we define the derivative of a single variable function. We take our function, our r of t, we have our point at, we're at r of t, and then we consider r of t plus h. So this is r of t, here's r of t plus h, and we let this distance get smaller and smaller, but we divide by the magnitude of the distance. Right? So we divide by this, not the magnitude of the distance, sorry, we divide by that time interval. So as that time interval gets smaller and smaller, this vector gets smaller and smaller. Does that limit exist? Does that limit, this difference get smaller, but does the quotient of those two things, the vector in that direction, divided by the time interval difference? How different is that? Does that have a limit? If that has a limit, that's defined to be the derivative. And there's a simple way to do this, which is take the derivatives of each of the components of this vector function. And you can start to see what's happening here is that as you get closer and closer, right? So if h is big, we've got this vector, but as it gets closer and closer, this vector, if we normalize it by this time, this r prime is going to be a vector that's tangent to the curve. So this should feel somewhat comfortable because when we're taking the derivative of a single variable function, we often use the derivative to be the slope of the tangent line. So it should feel comfortable that when we take the derivative of a vector valued function, that should be related to the slope of this tangent line, the slope of the tangent line to the curve. But what does that mean in higher dimensions? Probably the best thing to think about is it's representing this vector. It's representing that direction. So as you move along a curve, you're following this direction that the curve is taking, and this r primed is that direction that's tangent to the curve. We can do some integration. So just like we can take the derivative of each of the components, we can integrate each of the components. This will be helpful in the next video when we talk about velocity and either taking the derivative to get velocity and acceleration, or taking integrals to go backwards, to go to position. So we're going to integrate as well. If we want to integrate a vector function, we'll integrate each of the components of the vector function. Also, assuming we can do this. And just like when you're dealing with definite integrals, you get a number, right? You're getting a number, you're getting a vector here. That's a bunch of numbers. If you're doing an indefinite integral, you get a constant of integration. So if we're integrating 2 cosine of t, the integral of cosine is sine, so 2 sine of t. The integral of sine of t is negative cosine of t. The integral of 2t is t squared over 2. Don't forget your constant of integration, which there's a constant for the x-coordinate, there's a constant for the y-coordinate, there's a constant for the z-coordinate. All right, so let's apply this to find the derivative of the tangent line to a bunch of different curves. We'll do one in 3 dimensions, we'll do one in 2 dimensions. All right, so consider this helix 2 cosine of t, sine of t, comma t. So notice that this isn't exactly the helix that we talked about before. In the helix that we talked about before, we had cosine of t, sine of tt. But this multiple of 2 is doing a dilation in the x direction. So instead of being a circle going up around and around, we instead have an oval going up and around and around. And the stretch is in the x direction, so maybe I'll draw it this way. All right, so here we have a helix, we have a vector equation, and we have a point on the vector equation, vector function. And given this point that's on the vector function, we need to find the equation of the tangent line to the helix. Okay, so this is where we go and we say, all right, we need to find the equation of a line. To find the equation of a line, we need a point and we need a direction. So we have our point, so we need our direction. So we want a tangent line, we need a point, we need a direction. And the point we have, the direction is in the direction of the derivative of r of t, which is a function. So we'll need to figure out exactly what part of the derivative we need. Okay, so here's our game plan. Let's find the t that goes through our point, the time when our curve goes through our point. We'll find the tangent vector to the curve at that point and use that to write the equation of our line. Okay, so we want to find t star such that 2 cosine of t, comma sine of t, comma t is equal to 0, 1, pi over 2. All right, so this says we need something when 2 cosine of t is equal to 0 and sine of t is equal to 1 and t is equal to pi over 2. That last equation is super simple to solve. What is a t when t is equal to pi over 2? Well, t star here is pi over 2. If we plug this t value into here, here, and here, we get the correct vector. Good. We know that t star is pi over 2. So now we find the tangent vector, the derivative of r of t. So we get what? We get the derivative, take the derivative of 2 cosine of t sine of t t. And what do we get? We get negative 2 sine of t cosine of t comma 1. And now we have to do r primed of pi over 2. So now we plug in pi over 2 into this equation. What do we get? So negative 2 times 1 comma 0 comma 1, which is negative 2, 0, 1. And so the equation of the line is going to be our point, 0, 1, pi over 2, plus t times this vector, negative 2, 0, 1. L of t is equal to this. That's the equation of our line. All right, let's do another example, this time in 2 dimensions. So here we have a curve that has the equation t squared comma t cubed minus 3t. Okay, what does that curve look like? Maybe we were trying to find the tangent line to this curve at 3 comma 0. Maybe we should come up with a picture of that so that we know what we're talking about. So let's go over to Mathematica, and this is a parametric plot. Parametric plot of t squared comma t cubed minus 3t, and t maybe we'll go from negative 5 to 5, and maybe plot range. Since we care about 3, 0, let's just make the plot range 5. So this is our curve. When t is negative, this is negative. So that means we're coming up from here, we're going around here, we're going up this way, and we're asking what is the tangent line here at 3, 0. Oh, but wait, there's 2 tangent lines at 3, 0. There's the one when the curve is coming up this way, and there's the one when the curve is coming around this way. Whoa. All right, that could happen. So let's go and calculate it. But it's good to know that there's 2 of them. All right, so let's go back over here. So similar to what we did before, which is to say, all right, we need to figure out what the time is. So we want t squared to be equal to 3 and t cubed minus 3t to be equal to 0. So if t squared is equal to 3, then t is equal to plus or minus the square root of 3. Oh, there's our plus or minus. That's our 2 different points when it goes through. And we can check to make sure both of those work here. So we could do square root of 3 cubed minus 3 times plus or minus square root of 3. So what's that? That's 3. So plus or minus square root of 3 minus plus or minus 3 square root of 3, which is indeed 0. Okay, so that means that these are our 2 special points, t equals plus root 3, t equals minus root 3. Those are our 2 special points that we care about. So now if we're going to write the vector form, we need to take the derivative. So let's do r primed of t is equal to 2t comma 3t squared minus 3. And now we need to plug in the values. So when we plug in root 3, we get 2 root 3 comma 3 minus, so 9. So root 3 squared is 3, times 3 is 9, minus 3 is 6. So this is when t is equal to plus root 3, we get this. When t is equal to minus root 3, we get negative 2 root 3 comma 6. These are our two vectors. And so what this means is that the equation of the line is going to be our initial point, 3, 0. So L1 of t is 3, 0 plus 2 root 3 comma 6 t, and L2 of t is same point, 3 comma 0 plus negative 2 root 3 comma 6 t. All right, and these are the equations of the two tangent lines to the curve at 3, 0. Last, let's say we wanted maybe the point slope form of this line. Right here we've come up with the vector equation, but this is in 2 dimensions. We could actually come up with what the equation of the line is. So how do we do that? So to find the slope of the line, well, what we'll do is we'll say the slope of the line is dy dx, and these are represented in terms of t, so we can figure out what the change of y with respect to t is, the change of x with respect to t, and divide the two of them. Right, and we've calculated these. Here, dy dt is 6 divided by 2 root 3. So dy dt is 6, dx dt is 2 root 3. So the slope here is going to be then 6 divided by 2 is 3, divided by root 3 is positive root 3. This is the slope of the line. And so that means that we could write this equation as y minus 0 equals root 3 times x minus 3. And the other equation we could write as y minus 0 equals negative root 3 times x minus 3. So if we wanted to write these in the y equals mx plus b form or y equals point slope form, we could write those equations in that way using this understanding of slope, our classic understanding of what slope means, as the ratio of the slopes of our two different components. All right, that's enough for now. See you shortly.